Okay, so we're looking at Tuesday or Wednesday for this gateway test on these derivatives. We still have a couple things to do yet that we'll get into the next couple days. So it's kind of depend. Kind of prepare like it's Tuesday, but it might be Wednesday. So we'll kind of see. I'm trying to decide that tomorrow, but I may not know for sure till Monday. So we did a lot yesterday. There were a lot of problems, and so you may or may not got a chance to get through all of them. So what do you have? Let's start with 3.1 on the product rule quotient rule. What questions do you have, James? 19. Is that the one with the 1 minus x cubed? Okay. I apologize for that one. I meant to give you but even then, it's a good one worth doing. Even if I had given you this, it would be worthwhile talking about. That one there. That one. Okay. So the idea was to simplify and then to do it with the quotient rule. And so, but how do you simplify that? Well, to simplify that, you would have to go back to Algebra 2 class and remember the difference of cubes, the factoring pattern. I don't expect you to memorize that, okay? You may have done it in Algebra 2, I don't know. But a cubed, because that's what you have on top here. A cubed minus b cubed is a minus b times a squared plus ab plus b squared. That's the difference of cubes factoring pattern, okay? And so this would factor in, so on the part where you were simplifying, this would factor into 1 minus x, and then 1 plus 1x plus x squared, all over 1 minus x, okay? And then those would cancel, and we'd be left with that. Well, then what's f prime got to be? One plus 2x, right? Derivative of 1 would be 0, derivative that's 1, derivative that's 2x, okay? So it works really nice if you can simplify it first. If I gave you that one on the gateway test, which I could, for sure, if you knew the cube, it's just like a lot of things that we say, you know, you can memorize this, you don't have to memorize. I mean, there's certain things you better memorize or you better have. But then there are other things where if you have them memorized, it makes life easy, right? But if you don't, then what do you do? And so if you had that memorized, that would make that problem a lot easier. Okay, but let's say you did it. Okay, so you do the quotient rule. All right, so the quotient rule, so this is just good practice on the quotient rule. So the quotient rule is, remember the top would be what? Top, up here. That 2x squared. Negative 3x squared, right? The 1 derivative, that's 0. Bring that down, so it would be negative 3x squared times the bottom left alone say it again. See, when I wrote that, like it should have been like nails on the chalk. Of course, when was the last time you were in a classroom with a chalkboard? Anybody? Ever in your life? Okay, well, the old fingernails, the old fingernails on the chalkboard, and you get goosebumps and your skin crawls, and it's like, that's what you should have been doing when I wrote that. Right? You should have been bothered. There should have been red lights flashing. That's awful, what I just wrote right there. Okay? If you write it like that, that is going to cause you great trouble on the gateway test. Okay? This has got to have parentheses around. Now, could you write it without the parentheses and still know, and then later come down and distribute and know that you're supposed to? I suppose. And there's some of you maybe would get away with that. But, no, I mean, trust me. I've graded a lot of gateway tests, and that is a disaster. Okay, so anyway, the bottom left alone minus the top left alone times the derivative of the bottom. Negative 1. Okay, all over the bottom square. Right? Okay, so what do we do now? So if this was a gateway test and you did not remember this factoring pattern, or more likely I give you one that doesn't even have a factoring pattern that you could simplify, you're forced to do the quotient rule, right? This would not be acceptable to stop right here. Okay, so what do you do? What do you do? Braylon, what do you do? Right here. Okay. And what about this -1 over here? Couldn't that come around here in front, and then wouldn't that just turn to a plus? So, and then it turns out that those parentheses then don't matter at that point, right? Now it's just plus that. Okay. So I'm going to have -3x squared plus 3x cubed plus 1 minus x cubed, all over 1 minus x quantity squared. Simplify the top because I'm hoping some things, the reason I always distribute out, FOIL out the top, because I'm hoping to combine some like terms, maybe some things disappear, maybe some things factor and cancel, you just never know. That's the kind of obvious simplifying I expect you to do. Okay? Now, I usually don't FOIL out the bottom because it usually doesn't do much good. What you're trying to do is get some things to happen up here so you can maybe factor and then cancel. So you want to leave the bottom factor so that you can do that. Now, it doesn't have a common factor. Okay? So I will be perfectly okay with you stopping right here on the gateway test. Because to me, you've done the obvious simplifying. Okay? Now, you might be wondering, what in the world? We're supposed to get the same thing. Well, if you remember Algebra 2 class, and 2x, well, this would be 1 minus 2x plus x squared, right, on the bottom. So in Algebra 2 class, you did this. Oops. Remember long division and synthetic substitution and stuff like that in Algebra 2? Right? It turns out, since we do think that this is equal to this, it does turn out that we can divide those. And the way you did that, you're not going to do this on the unit test, right? You're going to be able to stop right here. And go ahead and get your calculators out while I do this. But then we would look at this and we would say, okay, x squared goes into 2x cubed. Well, that would be 2x. And then we distribute that. That'd be 2x cubed. And that would be minus 4x, 4x squared. And then that would be a plus 2x right there. And then we would subtract those, and those would disappear. And -3 minus -4 would be -3 plus 4. That'd be 1x squared. And then plus 2x. Oh, no, I'm minusing. That'd be 0 minus 2x. So that's a minus 2x plus 1. Oh, look at that. X squared minus 2x plus 1. That goes into there one time, positive 1. So 1 times x squared, 1 times minus 2x, 1 times 1, subtract 0, 0, 0. Oh yeah, it divides. And you get 2x plus 1, which is the same thing as that. When you're checking your work and doing this at home, what I would do is what I showed you a while back. The way you can check this is I'm not going to type it in right now, but just don't do a solve. Well, you could do a solve, and you'll just get true, but you don't have to do a solve. You can just type this equals 2x plus 1. Hit enter, and you get true. Okay? So your answer, and you think, or the back of the book, or whatever, or maybe you did the derivative on your calculator, right? You just do the derivative on your calculator like we were doing yesterday. Like, who was our presenter yesterday? Who was doing that yesterday? Braylon. Braylon was typing A, just do the derivative. It's going to give you 2x plus 1. You work it out, and you get this, and you go, oh, are those the same? And then type in take what the calculator did equals what you got, and see if it says true. Now, most of the time that works. Sometimes there might be some issues, but most of the time you can at least feel good about it. If you don't, come in and ask me where you went wrong or whatever. Okay? That's a good problem to do just because of all this algebra and now listen, there's going to be 10 problems. There's not going to be 10 of them that have that much algebra and simplifying to do. if you're trying to simplify and combine terms, cancel, and do all this algebra, more than about 3 of the problems, you're doing way too much, right? You're trying to do too much. So some people get hung up on the simplifying part of this, okay? Because they struggle with it and they overdo it, and then you end up making a mess of things, okay? So it's going to be on there. There'll be some where you have to do a little bit of this simplifying kind of stuff, distributing or combining terms or something. But then there's going to be plenty of them where you just pretty much do the rule, and then you're pretty much done, okay? And there's a mixture of easier and medium and kind of harder ones, you know, that kind of thing. Again, that's subjective. Depends on, you know, who's doing it, whether they think it's easier or harder or whatever. But, all right, what else? Who else? Somebody else had one, I think. Somebody else had one? Yeah, Sam?
42.
42. Is this still on that product quotient rule one page?
Yeah.
Okay. Let me see here.
Oh, it's actually 42. Yeah, we did. Yep. We did.
Let me pull this up, I think I got it. Is that 43? Is that one we did?
Yeah.
But we did 42 also? What was 40? What did 42 say? Big giant man. Oh, the big chart. Yeah, okay. So, but they tell you about, so you're filling in the chart for H prime and J prime, right? So H prime is going to be F prime G plus FG prime, right? And J prime is going to be F prime G minus FG prime all over G squared. Is that right? Okay, I mean, that's your product and quotient rule. So when you have to fill in H prime and negative 2, so, right, that top one in the table, so H prime of negative 2 is going to be F prime at negative 2 times G of negative 2 plus F of negative 2 times G prime of negative 2, right? So F prime of negative 2, so we read the table, that's negative 1. G of negative 2, that's negative 3. Plus F of negative 2, that's 1. And then G prime of negative 2, that's 4. And so we get 3 plus 4, we get 7. Does that make sense? And then that's how you fill the rest of that table. So you go to that row and you just plug it in to those. Okay? All right, what else? 23. Did I have a couple? So 23. What was 23, Jason?
Square root of x times L of x.
Okay, so y equals, or f equals, or h, whatever it is. Okay, so the derivative. Okay, so what's your question specifically?
Well, I got to a certain point and I basically didn't know what to simplify.
Okay, right, that's a common question, right? That's one of the things we're learning here is what is simplified? What's the obvious simplified? What's obvious to me is not obvious to you. Over the next several days, that will get more obvious. Okay, derivative of the first, 1/2 x to the negative 1/2, right? ln x left alone. Plus x to the 1/2 left alone, ln x derivative is 1 over x, right? Product, okay? Simplify. Now, you go back to Algebra 2 class, if you were in Mrs. Andreessen's class, I'm guessing when you were working with radicals, you changed them to powers. If the original problem was radicals, you probably would change to powers, do some work, but you probably had to move them back to radicals at the end, right? If the original problem is in radicals, you should have your answer in radicals. That's reasonable, but we're not going to do that. It depends on the problem. If I was doing the derivative and setting it equal to 0 and solving it without a calculator, then I probably would want to go back to radicals, and that would probably be a better way to solve the problem. Okay? It would probably make life easier for me. But all I'm doing here is writing down what y prime is. So I want to do some basic simplifying, and then I'll stop. So to me, There is nothing else to do on this first part. But my guess is what they did in the back of the book is they took this negative power, flipped it to the bottom, and turned it back to square root, right? So you x to the negative 1/2, go down to the bottom with the 2 is x to the 1/2, which is square root. So my guess is they probably wrote it like this, with an times ln x, which you actually could put up here, and that'd be fine, right? But I would say you don't need to. That's fine. If you want to do that, you can. The obvious simplifying to me is right here, right? That needs to be dealt with. I mean, that would be like leaving x squared times x cubed and just leave it, right? That, to me, that's obvious x to the 5th. You need to make that x to the 5th. Now, this may not be quite that obvious, but it's pretty close, right? This is x to the 1/2 times x to the negative 1, which is what? X to the negative 1/2. Or you can make an x to the 1/2 over x, whatever, and then subtract the powers, right? But it's x to the negative 1/2. So that, to me, needs to be done. So that would be a fine answer to me, right? Now, you want to factor out the x to the negative 1/2? I say there's no reason, right? If you factor something out, it's so you can then cancel it with something, but there's nothing to cancel. So I wouldn't bother factoring. I would just leave it, just like that. Okay, but if you want to go back to square roots, right, then they maybe put it together and got a common denominator maybe, right? There's all kinds of things we can do after this, right? We can do this, and then this would be 1 over square root of x, and then, so then we could multiply the top and bottom by 2, and now we can put it back together, right? Ln x plus 2 over 2 square root of x, right? If I was doing the derivative and setting it equal to 0, then yeah, I would probably want to do that, because now that makes that easier to solve, probably, right? So, will we need this ability to maybe rewrite this in a different way and so forth? Very well could down the road, right? So it's certainly something we should, an ability we should have. But for right now, I'm mostly interested in doing the derivative rule correctly, all right, which is to here, and then with some obvious combining like terms, power rule, or, laws of exponents kind of stuff there. All right, good question though. These are the kind of things we need. That's why we might not do this even till Wednesday, is just because we got to get through. We got to practice these. We got to see it. Okay, but you got to put time in with it. All right, what else? Anything else? Yeah, Jake. 31. Yeah, I was working with somebody this morning on that one, and that seemed like a good one. What was that one again?
X plus 1 squared.
Oh, is that on top? Is this a fraction one? X plus 1 squared.
Over x squared plus 1.
X squared plus 1. Okay, and this is another one that's going to just have a lot of kind of algebra to it and so forth. So when I go to do the derivative, so let's review our quotient rules. So the derivative of the top, so we bring the 2 down in front. The inside stays the same. So it's kind of a chain rule, but we haven't really done the chain rule yet. That's the next section. But we have talked about this x plus 1 is a shift, and there's nothing to kick out or anything. So we do 2x plus 1 to the first, which I won't write, so nothing to kick out. And then times the bottom left alone, so we're going to put that in parentheses as well, minus the top left alone, okay, times the derivative of the bottom, which would be 2x, right, all over the bottom square. All right, now, right, bottom square. All right, whenever I see one like this, I want to FOIL out the top because there might be some like terms, some nice things might happen, and at the end they may not. But that's what we should do. So we wouldn't want to leave this one like this. And so I would go ahead and FOIL this. And so here I might just go out to the side and do that x cubed. This would be 1x. The inside would be x squared. Let me do that. So x squared and a 1x and then plus a 1. So that, and then when I put a 2 on that, so I'm going to get 2x cubed plus 2x squared plus 2x plus 1 when I FOIL that. Throw the 2 in there. Here, I'm going to have to FOIL that, so that's going to be x squared plus 2x plus 1, and then I distribute a 2x to that, right? I distributed 2x to that, so it's going to be 2x cubed plus 4x squared plus 2x. I think I did that right. And then that's all going to have a minus in front of it, right? That's all going to have a minus in front of that, so they're all going to turn negative. So I'm going to have a negative 2x cubed, and negative 4x squared, and a negative 2x. So a lot of times I'll go kind of off to the side, do some of that kind of stuff. But be neat with your work so you kind of don't lose track of things. And so I foiled that, distributed that, and then I remembered I had to minus all of it. Well, some nice things do kind of happen there. And so I get negative 2x squared. Those go away. That's nice. Plus 1. So that's kind of what I was hoping would happen, is there'd be some things kind of disappear and so forth. I feel like I missed something. What's that?
It should be plus 2.
Where? Oh, right here. Right on the first one. 2, 2, 2, and I forgot a 2 on there. Okay, that should have been a 2 right there. Okay, there we go. All right, now, if it wouldn't have been, then I'd have pretty much been done, right? If that would have been a 2. Now, the reason I think you say, well, factor out a 2, but then nothing nice happens. Actually, I'm not sure anything nice is going to happen anyway. I could take out a 2, and that gives me negative x squared plus 1. Yeah, nothing really nice. I thought maybe I was going to get something to cancel here. But because this is 1 minus x squared, which turns into 1 plus x, 1 minus x. But unfortunately, that does not factor, right? That's not x plus 1, x plus 1, right? That doesn't work. So unfortunately, this doesn't factor out or anything, and none of these will cancel because it's got that x squared. So taking out the 2 doesn't really do me a whole lot, so I would just stop it. Okay? But you could factor those things. All right? I think does that look like what they have in the back? Okay. All right. But yeah, so a little bit like the one we did earlier. I was on another thing, but on 19, just this on a quotient rule with algebra ones. Now, when you get exponentials and logs and sines and stuff in a quotient rule, a lot of times, when you get a mixture of the function types, a lot of times then you can't. There's not a lot of simplifying that can be done on a quotient rule. But it was just algebra stuff, just plain old x's and powers. Then you can get into some of this simplifying. Okay? All right? Anything else? 49. 39. 39. What do you have on 39? What's 39?
Wants you to determine whether g of x is an antiderivative, and it's, or the big G.
Oh, yeah. Okay. Yeah. So this is good. This is good review of our whole just notation stuff. Determine whether big G is an antiderivative. So when we were doing antiderivatives, getting ready for the last quiz, we said if big G is the antiderivative, how could you check it? Do the derivative of big G and see if you get little g. So that's what you would do on 39. So on 39, you're going to take big G. So read that to me there, Chris. What's big G say?
Big G is 2 minus e to the 2x times cosine x.
Okay, so do the derivative of big G, which should be little g, right? And let's see if that's what we get. So the derivative of 2 is 0. And then here's what I would always do. This minus sign I would treat as a negative that is attached to the e. So now when I do my u and my v for my product rule here, I'll always keep that negative with that. Otherwise, if I did this as my u and this is my v, then I've got to remember to distribute that negative, and invariably we forget. So attach that negative as part of that first term, and like add the opposite kind of thing, and then you'll be better off. So the derivative of the first thing would be negative 2 e to the 2x, cosine left alone. And then plus the first left alone, which will turn it to a negative, e to the 2x. So that way I didn't have to think about distributing it. I just thought of the negative attached to that. And then the derivative of cosine is, which will turn that to positive. So negative sign, because I'm timesing negative sign, so that negative times negative will turn to positive. And we'll get that. And then I look at their little g, and is that the same thing? It looks like it is. It's just I got to flip those around, right? And there's my minus. And so there you go. And so you say, yep, big G is the antiderivative of little g. And we check it by doing the derivative system. Okay? All right. Well, and so on that 42 through 48 section, I want to talk about that a little bit. Okay? And again, so I had, well, here's 43. Okay, so I'm going to do 43 and 48. Okay? So 43. Estimate h prime of 2 and h prime of 4, and they gave you the picture of little f, right? They gave you the picture of little f. So little f, or excuse me, h is this, right? So I went ahead and did my product rule. Okay, went ahead and did my product rule, got this. Okay, then h prime of 2 would be all this. Well, I need f of 2. Well, I can just read that right off the graph. F of 2 is negative 4, and so that's where I got that right there. And then I need f prime of 2. Well, that's going to be the slope of the f graph. Well, if you go to 2, right, it's at the vertex there, so the slope is 0. So that's where I got a 0 for that right there. And the rest of those I just already have. So you just multiply those out and I get that. Okay? On 4, when I plug in my 4 here to get f of 4, I just read it right off the graph. That was 0 right there. And then I need f prime of 4, and that's where we would just sketch in our tangent line and kind of estimate the slope, and I estimated it to be about that. Okay? So, that worked out to be that. Okay? Then when you get to 48, and so the rest of those are very similar, is m increasing at 3, so this is what we were talking about earlier, is m. Oh. So here's h prime h. Oh, this must be, this is 45 actually. This is 45. 45 says, is h concave up at negative 1/2? Well, for h to be concave up, what do you need? Second derivative, positive, right? So I needed the second derivative. So I did h prime, was my product rule. That's what I had on the page before. And now what do you got to do? You got to do product rule and another product rule. Okay? That's fine. So I did it. So there's one product rule. There's a second product rule. Okay? And now I just have to plug in a negative 0.5 everywhere. Okay? So I got to do f of negative 0.5. So I got to look on the graph for that value. I got to go to f prime at negative 0.5. So I had to get that value. I think I put negative 4 as that slope right there. And that showed up 2 different places, okay, over here. And then I had to get f double prime. Now that's the question. How do you go, so look at the f graph on page 167. Go over to negative 0.5 on the f graph. And how can you tell what f double prime is? And notice I've left it blank here. So on page 167, look at the f graph, go over to negative 0.5, go up to the graph. What can you tell me about f double prime? F prime would be the slope. What's f double prime? What's f double prime measure? Concavity. But we've never talked about how to measure it, right? Well, think of it this way. If you have an f double prime of 2 compared to an f double prime of 1, that means the one that has an f double prime of 2 has more concavity. It's more curvy, right? Just like a slope of 2 is steeper than the slope of 1. An f double prime of 2 is more curved than an f double prime of 1. But what concavity do we have on the f graph? It's concave up. So we know f double prime is what? On the f graph, we know f double prime is positive. So I'm just going to put a positive value there. I don't really know. We have no way of measuring the curviness of it. So I'm not going to get into that, and I don't think it's necessary because when we fill in everything else, we get 5 plus 4 plus 4. And what do we know about this? It's positive, right? And all we're trying to figure out here in 45 is h concave up. is H, not F, is H concave up? Well, H is concave up if its second derivative is positive. Well, we can clearly see that it's going to be positive. Okay, but so that was a nice problem to review your chart kind of ideas, but it's a lot about product rule and plugging in values, and it's just an interesting, I think, an interesting way to approach that problem, and still at the same time practice your product rule. Okay, at 48, then they give you the M function, which means we need quotient rule, but it says is M increasing at 3? Well, that's really asking is M prime positive? Is M prime positive? So we do the quotient. Now I'm not going to give you any like this on the gateway test, right? But they just tell you some unknown F function is up here on top. So I go ahead and do my quotient rule, right? Do everything like we would normally do, and then plug in a 3, right? So F prime of 3 would be the slope at 3, and we can estimate what that is. It looks like it's, I don't know, roughly 2, and this is 3 squared is 9 plus 1 is 10. So 2 times 10 is 20, okay? And over here, F of 3, we just read off of there, that's negative 3. And then 2 times 3 is 6. So minus a negative 18 would be plus 18. And down here, we get 10 squared is 100. So clearly, this is a positive value. So M prime at 3 is positive, so M is increasing. Okay, but again, the main part of this problem is, can you do the quotient? The rest of it's just plugging in values. So forth. Okay, 79. Okay, let's go through this problem here real quick. Okay, and then we'll get working on some chain rule stuff. Okay, and then we do have a new thing to talk about today. All right, so 79 was, so this is where we're headed with this in chapter 4. Okay, here's where once we learn all our derivative rules, this is what we'll see in our midterm and our final, and this is what we get to actually use this stuff. This is what we just got done doing in chapter 2 is max-min problems. So they want the max and the min values, and then also talks about an inflection point. I'll leave that for you. But so we've got a product rule. So derivative first times this left alone plus the derivative of that times derivative cosine, or this left alone derivative cosine, which is negative sign, so I put the negative there. And we got to set that equal to 0. Oh, by the way, on the quiz, okay, and well, you'll see it when we go over it. Maybe we get to tomorrow. A lot of you on the max-min problems put the derivative, but you never put equals 0. I didn't take off for it this time, okay? But if you're solving an equation, you've got to have the equation on your paper, okay? You can't just have the derivative. You're solving the derivative equals 0. You've got to have that written down, okay? All right, so anyway, I would factor, let's assume this is no calculator right now, okay? So we would take out an e to the x, which would give me this, and so either this equals 0 or this equals 0. Well, when does e to the x equal 0? Never. Here's e to the x. It's never 0, okay? So we can ignore that. When is this 0? Well, when cosine is equal to sine would be a good way to think about that. When does cosine equal sine? Pi fourths. Never, right? The other time's down here, right? When they're both negative, right? And that's not between 0 and pi. So it looks like x equals pi fourths, right? Is the time that cosine is equal to sine. So there's our stationary point. So our list of candidates would be our endpoints and then our stationary point right here. Okay, now you get into, well, now maybe at this point you would have a calculator because you got to plug them into here. Now 0 is easy. E to the 0 is 1. Cosine of 0 is 1. Okay, pi, that's e to the pi, whatever that is. 2.718 raised to the 3.14. Times cosine of pi, which is negative 1. So I don't know, 2, almost 3 raised to 3. That's like 3 cubed. I mean, that's what, 27. I mean, that's negative like 20 something. That's pretty big negative value. And then pi fourths, e to the pi fourths times cosine of pi fourths, which would be root 2 over 2. Might, that's, I would guess that's bigger than 1, but I don't know. that's where we might want a calculator. Or we can do a number line to see it's probably increasing until there, then decreasing. So this probably is bigger, this is probably a bigger value, but we can cheat right now, use our calculator, whatever. So max, min, okay? So, also one other comment I'll make right now. When you give your answer, when it says what is the max value, so let's say the max value is right here. Way too many people, there's another one I didn't count off on this time. Way too many people said the max is at x equals pi fourths. That's not what we want. If it says what is the max value, they want this answer right here. Okay? Local max min, they say where is the local max min, then they want the x value. What is the max value? They want the value. They want that right there. Okay? All right. But that's just showing you a problem where we have to use the product rule, and then we can go on and do the stuff we've done before. All right, what about page, section 3.2? What do you got over there? Yes. Number 12. I've got a couple on here, like 21 and stuff like that, but you got it before that. Number 12. Okay, read it to me.
1 divided by the square root of x squared plus e to the negative x.
Okay, first of all, I would never do a quotient rule when there's a constant on the top. Okay, now nobody asked about this one, but this is one I talked with somebody this morning about number 17 on the other page. On number 17, it was 1 over e to the 2x. Okay, now you could do a quotient rule here, but this is way better to do this. Okay, now the reason it's not good to do the quotient rule is the part we always screw up is this. Well, as a matter of fact, let me give you even a better example. What if you have 4x squared? You could make an argument that you could do a product rule on 4x squared, right? 4 is a function, x squared is a function. Now, it'd be silly to do it because we know the answer is supposed to be what? 8x, okay? But here's how you would do the product rule. The product rule would be derivative of this, which is 0, and that's the part we always mess up because we don't put a 0 there, okay? Because normally when we do 4x squared, we don't put a 0, we just do 8x. We leave the 4 there, and so some reason people want to do that. If you're going to do the product rule, which would be silly, you would do the derivative of 4 is 0, x squared left alone, plus the 4 left alone, and then derivative of x squared, which is 2x, and so you get 8x, okay? So it'd be silly to do the product rule, but you could. Okay, well, it's the same thing here. When you do the top part, the derivative of 1 is 0, and then times the bottom left alone minus, and then you get the 0 in here, and it just fouls things up. So it's way better to do that. Okay, same thing on this one. So it's way better. So if you have an x up here, then yes, I would do the quotient. But if it's a 1 or a 7 or something else, then I would always flip this up here. So this is going to be x squared plus e to the negative 3x to the negative 1/2. So I would always do that. Okay? Now, when we do our y prime, so we're going to bring the negative 1/2 down in front. We're going to leave the inside alone. We're going to drop that by 1, which would be what? Negative 1/2 minus 2/2 is negative 3/2. And then times, remember I said put a big set of parentheses because you don't want to mess that up by not having parentheses, the derivative of this. So now we're just looking at the red thing. So now the derivative of that would be 2x. And then we're going to kick out a negative 3 e to the negative 3x, right? Because we always know we got a number in there, we kick that out. Now, I would then leave that alone. You're done. So I don't know if that was your question, Haley, or was it about writing it this way first? It's about simplifying. See, to me, there's nothing. Now, what could I do? I could flip this down to the bottom with that 2. So I could have a negative 1. I could have this, right, all over, and then I'd have a 2 down here, and then this would be x squared plus e to the negative 3x to the positive 3/2. But again, that's fine, but it doesn't really do much for it. So I would be fine with you just leaving that. Okay, I would be fine with you just leaving it here. To me, do you see how that's just rearranging? I just moved that down. It didn't cancel anything. It didn't combine anything. I just rearranged. You can distribute the negative one through there. That'd be fine. But again, not really necessary. See, to me, if you have a problem like this, where it ends up being this, right? That's fine. You want to distribute the 3? Okay, it doesn't really do it much for you. Yeah, that's fine. You can distribute the 3, right? Same thing if it comes out to be this. I would just leave it. You can take out the 3 if you want, but it doesn't do much. Right? Either way's fine. Okay?
So you'd be fine with leaving it black.
This, you bring a new color. So this would be fine. Right here. That would be fine. Okay? So that's what I was saying. If you're doing a whole bunch of simplifying and rearranging, you're thinking about it too much. Right? A lot of times it's going to be boom, 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 do the 3 steps, done. Right? Done. What else? 15? What was 15?
Cosine squared.
Of this right here. Okay? So that's very similar to the one we did yesterday, where you better write it this way first. Right? So, step 1. Derivative of the outside. Bring the 2 down. Leave the cosine alone to the first. Right? Times. Big parenthesis. Right? And I need it, but I'm going to put it. So now I'm on to step 3. Derivative of the outside, step 1. Leave the inside alone, step 2. Step 3, derivative of the inside. So I'm ready to do the derivative of the inside. But then I look at that and I say, oh, that's kind of messy. But now I'm just focused on just the red thing, right? Focused on just the red thing. I got my parentheses here where it goes, so I don't have to worry about that. I'll focus on just the red thing. So now the red thing, I got an inside on that. Okay, so I'm doing the derivative of the outside, which is negative sign, step 1. Leave the inside alone, step 2, times the derivative of the inside, which is, and you could put a set of parentheses there, 3x squared. Now, parentheses weren't really necessary because I didn't have any plus signs in there. That's the key. When you have multiple terms, you got to group them with plus sign, parentheses. I didn't have that, so I probably don't need a lot of those parentheses there. But, so now, since there are no powers on the outside of anything, these are all just things that are multiplied. That's one thing, that's one thing, that's one thing, that's one thing. I've got 4 things that are multiplied, A, B, C, D. I can rearrange them however I want, so I better put this negative with this 3, with this 2. That makes a negative 6. And then I've got this x squared, and then I've got this cosine, and then I've got this sine. So that should be your final. It would not be okay to leave this alone. Okay? Anything else before number 21? Yes? What's it say?
Square root of 2 plus sine x over 2 plus sine.
Square root of all that? Just that. Just this right here. Okay? So I would immediately write that like this. Right? So the derivative would be 1/2 in front, 2 plus sine x to the negative 1/2. So step 1, bring down to 1/2, drop it to a negative 1/2, power rule. Step 2, leave the inside alone. Step 3, multiply the derivative inside. Put a big set of parentheses. Now all I care about is the blue thing. So now I'm just looking at the blue thing, and that's going to be 0 plus cosine. Now, there's nothing I can do other than rearrange. I could I could take this negative power, flip the whole thing down to the bottom if I wanted to, put the cosine on top, so I could do cosine x, and the bottom have a 2, and it would have a 2 plus sine x to the 1/2, which of course is square root, if you prefer that, right? But not necessary. You can stop there. Let's just rearrange. Okay? All right. 21 gets into that same stuff I was doing earlier, just with the table, right? So they tell you H is this. So H prime is that. That's just the chain rule, derivative of the outside, right? So if you want to do H of 1, that'd be F of G of 1. Now, the one I really want to talk about is the graph one, so I'm gonna move on from that. But so you want to do H of 1, right? You do G of 1 first. So G of 1 is 4. So this becomes F of 4. So then you look up F of 4, and you get 3, right? On this one, you look up G of 1. We just said that was 4. So now you got F prime of 4 times G prime of 1, because X is 1. So now you just look those up. Okay, just look those up. All right. So now let's look at the, and then 22, they just give you these values. So again, I'll just throw this up here. If you want to spend more time with it, you go back and look at the video and you can see. But just derivative of the outside is F prime, leave the inside alone, times the derivative of the inside, which is a great big old quotient rule. And then it's just a matter of plugging in a 1 everywhere. Just plugging in a 1 everywhere, and then look at it, or you don't have to look it up. They gave you all those values. So they give you a whole bunch of those values. You just plug them in. Okay, so that kind of stuff is going to show up on some later stuff we do, but not on this quiz we do now. Okay, so let's go to 26. I want to talk about 26. Okay, so 26, you got this F graph here. Okay, and it says G of X is equal to F of X squared. So, according to our chain rule, derivative of the outside is F prime, leave the inside alone, X squared, times the derivative of the inside, 2X. So there's G prime right there. Okay, derivative of the outside, F prime, leave the inside alone, times the derivative of the inside. Three steps. Where does G prime equal 0? Right? Well, either when that is 0 or when that is 0. So let's write that down. Okay, well, I'll do this one for you. So there's 1. Where is this 0? What would you even look for? Well, right, so what do you mean by that? Where on that picture, this is the F graph, right? So on page 176, where down on that picture are you looking? At the vertex, right? Because that's the F graph. And so forget the X squared, right? That's what those people are. The question is just, where is F prime 0? Well, that's at 2. Now, this has never been important before, but it is now. Normally, we would say when X is 2. Well, that's because normally we have F prime of X here. But we don't. So now let's use the word input instead, right? So when is F prime 0? When the input is 2. Well, what's our input here? In other words, F prime of 2 is 0. You'd all agree with that? So doesn't X squared have to be 2? So what's X got to be? Plus or minus square root of 2. So there are 3 stationary points to the G function, right? That's what we're finding is the stationary points of the G function. Now, to get that, we use the F function, right? Because G prime was defined using the F function. Okay, so again, it just extends our knowledge a little bit on how we think about these things. Okay, in the past, it's just been F prime is 0, but this was always X on the inside, but it could be something. Okay, so it's when X is plus or minus 2. So for which values of X is G prime 0? Plus or minus root 2 or X equals 0. Okay, So that was all, well, no, it's not. Okay, let's get through this last one here. Where are the stationary points of H? So this is a very similar idea. So H is equal to this, so H prime would equal this, right? Derivative the outside, leave the inside alone. 3 steps, right? There it is. Where does H prime equal 0? Okay, well, it's when one of these two is 0, right? So let's attack this one first. When is G prime 0? Here's the G graph. When is G prime 0? Right there. And, I don't know, right there, let's say. Right? So what's that? At 1, 2.5. And negative 1.5. Okay, let's go with that. Now, where's this one 0? Now, this gets harder. Okay, so now forget the G for a minute. Just answer the question, where does F prime equal 0? There, and looks like there. So when the input is 0, 2, or 5, but what's our input? Right? F prime is 0 at 0, 2, and 5. That means when in here we have a 0, 2, or 5. So that means it's when G is 0, when G is 2, or when G is 5. Well, how do we find those? Those are the outputs over here. So when is G 0? Right? So that's at 1, 2, 3, 4. So negative 4, 1, and 5. So we got to put those along with those. When is G 2? There and there. So at 0 and negative 3. When is G 5? Never. Right? Okay. Well, our main focus, good problems, really make you think, and you know, probably should have just gave those separately as not as part of the gateway thing here, but you know, those are the kind of things that will be showing up as we keep going along too at various times when we look at these things. But for right now, I know our focus is more on the gateway. So I want to talk just a minute real quickly about website practice, because this is going to be part of your homework here. On our website, way down here on the left-hand side, it says web links. Now, unfortunately, Derivative Practice 2, and I'm kicking myself for not saving these PDFs. It just had some PDF files that had some practice, but all of a sudden it's not found anymore. And I went to this website. It was at Arizona State University. And this math teacher's still there, but for some reason on her website it doesn't have those anymore. So I'm gonna see if they've moved somewhere, see if I can find them. But it was just another option. But Derivative Practice 1 and Derivative Practice 3, those links do work. Okay? So, and you can actually search out, and you want to be careful because not all of them are that great. You can just type in Derivative Gateway in Google, and you can find all kinds of colleges have these web. That's all I did to find these. Now, some of these are fairly old now. But Derivative Practice 3 is from Jacksonville University, and so Math 140 is their Calc 1, and Math 41 is their Calc 2. Well, we're looking at Calc, we're basically Calc 1 right now. So if you go to Test 1 here, it'll pull up some derivative problems. Okay, now it's got about 8 of them. Now some of these we're not ready to do yet, like we haven't talked about arc sine, that's tomorrow. But most of these we could do. Okay, and so they're fairly simple. Now they give 8 of them and they have to get 7 right, is what that says there to pass. So these are, and it's got solutions here, and here's another one, and they're pretty similar. Okay, and so that's not a bad site to go for some extra practice. Okay, I wouldn't spend a lot of time on that one just yet. Probably we got enough in the book to keep us busy probably for a while. Derivative Practice 1 is kind of cool because you can give yourself all kinds of different ones. Like you can do difficulty level 1, 2, 3, 4, and then quite nasty. You can pick the different functions you want to practice. Okay, so if you just want to stick with e to the x, ln x, sine, cosine, and it's, of course, it's going to give polynomial and powers automatically. But you can pick some of these other ones. Don't worry about a lot of these down here. We'll talk about more of those later. So now you can just say, okay, start over. Okay, and so it gives you ln e to the x and do the derivative. Well, that's a silly one. Ln e to the x is x, and so that's just 1. But so you type in 1 and get your answer, whatever. Hit submit answer or skip it, right? 10x minus e. So these are pretty easy. Even 2 is pretty easy. Go to 3. So now you get something a little more difficult. It's got a product rule inside of it and a quotient rule, so that's a little more interesting. Okay, I wouldn't go, I don't quite nasty. I don't think I'd mess with quite nasty. We're not going to have anything like that, right? Probably not even level 4. 3 probably about as high as you go. But anyway, you can enter in your answers, see if you get them right. So it just makes up a lot of different. So that's not a bad place to get some extra practice too. Okay, so those links are on our website. Okay, all right. Let's get your notes out here and let's talk about this thing here a little bit today. So this is going to be on the gateway test. It's a way of finding the derivative of an implicitly defined relation. Now, a relation is like a function. It just doesn't have to have only one output for any one input. It's like a sideways parabola, right? Would be a relation, not a function, okay? Or a circle. Right? So any xy kind of equation is called a relation. And if we can't write it as just y equals, so if we write it as just y equals, that's an explicitly defined function. Okay, so y equals x squared minus 2x, or f of x equals x squared minus 2x. That's explicitly defined. Implicitly defined means the x's and y's are just all mixed up. The x's and y's are all mixed up. Now, maybe we can get the y by itself, like the first example I have here. We could get that y by itself, but it's possible, like the second one over there on the right, that you can't get the y by itself, no matter how hard you try. This is actually a hyperbola right there, kind of a tilted, slanted hyperbola. Okay? So, and it's not a function, and no matter how hard you try, you cannot get the y by itself. But think of a hyperbola. It's clearly got slopes at different values. I mean, if you had a graph that was a kind of a tilted hyperbola, and here was your xy coordinate, over here at x equals 4, there would be a slope here, and then there'd be another slope, up here. There'd be a y prime, and we should be able to find it. Okay? So how do we do that? Now the key here is, this is again another time when understanding what your input and your output variables are is important. We talked about we never have x prime if that's our input variable. The reason we never have x prime is that would just be dx over dx. That's just 1. That's a derivative of x with respect to x. That's just 1. So you never write x prime in these cases. But the derivative of y with respect to x, yeah, we write y prime. So we're going to have to think of this a little, right? We're going to have to really think about what's it mean to do the derivative of y. So far, all we've done is this. If you notice. Okay, let's go back to this problem number 7. Okay, so here you had this problem y equals. Well, what did we do? We took the right side and did the derivative. But you know what? We were also doing the derivative of the left side too. So if you think about it, what we were doing, we just said, well, do the derivative. That's what we were saying. But if you think about what we were doing, we were really doing it to both sides. We were saying do the derivative of both sides with respect to x is really what we were doing. So over here, do the derivative with respect to x means you do the chain rule. Over here, do the derivative of y with respect to x. That's just dy over dx. That's just y prime. The derivative of y is y prime. Make sense? I mean, it didn't even, it was so obvious we didn't even say it. Okay? But now it becomes important to say. Okay? Because it's not quite so obvious. All right? So x is our input, or what we call the independent variable, and y is the output, or the dependent variable, because y depends on what x is. Okay? So our inputs and outputs, it's important to know what's what. Okay, so let's take a couple of examples here. Okay? So, I give you this and I say do the derivative. Now, what does that really mean? It means with respect to what? If we do the derivative here with respect to x, then we would say y prime equals 1. And what we just did there is we did the derivative of y with respect to x. Here, we would be doing the derivative of y with respect to t. And so we would write y prime equals 1. And here we'd be doing the derivative of y with respect to z. We'd be doing dy dz. And we would write y prime equals 1. Right? It's the same thing. So it's identifying what's your output variable, what's your input variable. So y typically is our output variable, right? But we can have p if we're doing profit, or we can have other output variables, or population or something. But whatever. But typically it's y, right? And it's with respect to what variable. So sometimes I debate whether I should force you to use Leibniz notation. Maybe instead of y prime, I should always make you write dy over dt equals 1 here instead of y prime, right? And I don't mind lazy notation either, but understand it's with respect to what. All right, so now, what about a problem like this? The one on the left, okay? So we want to do the derivative of y with respect to x. Well, if I gave you this before we started this conversation and said, find y prime, what would you probably have done? Divide by 3, right? You'd probably divide by 3 on both sides and probably do it as I would write it 1/3 x cubed minus 1/3 x, and then do the derivative, right? That's probably what you'd have done, got y by itself. What I'm saying to you is you don't have to do that, right? We can just do the derivative of both sides. What do you think the derivative of 3y is? What do you think? 3 y prime. The y's can't disappear, right? It didn't disappear up here, right? When I said do the derivative here, did we write 1 over here for y? When we said do the derivative of y, did we write a 1? No, because we're doing the derivative of y with respect to x. The reason these are 1, because it'd be the derivative of x with respect to x. It'd be dx over dx. Well, that is 1. Okay? So when we did the derivative of y here, we got y prime. So what's the derivative of 3y? 3y prime. What's the rule? The 3 just hangs out in front while you do the derivative of the other thing. Well, what's the derivative of y? Y prime. You see that? It's the output variable. So the derivative of the output variable, you stick a prime on. Derivative of the input variable just becomes 1. Derivative of x is just 1. Okay? And then what do you get over here? 2x minus 1. Now you would divide by 3. Right? Which would be 2/3 x minus 1/3. Right? If we would have divided by 3 originally, we'd have had 1/3 x squared minus 1/3 x. And now if we do the derivative, bring the 2 down in front, that would be 2/3 x. And then derivative of this would just be 1/3. We get the same thing. Right? Okay, so now here's where it gets really interesting. So what if you had this? Well, we could square root both sides, right? We could do the square root of both sides, and we have a plus minus, because what you have here is a sideways parabola. Well, you don't even have sideways parabola, you have something weird going on. And it's not a function, so it'd be a plus minus. But so what you'd have is this whole thing to the 1/2 power. It'd be messy, you'd have to do all this, okay? It'd be messy, but we could do it, okay? And that's probably what we would choose to do, whatever. But I don't have to. I can just do the derivative of y squared. Now, hang on here, man, I want to see what my next screen is. Okay, so what is the derivative of y squared?
2y.
Well, no, isn't it gonna have to be 2y, isn't it? Aren't you gonna have to bring down the 2? I mean, we do the same derivative rules. The derivative rules are the same. What do you think it is? 2y prime? Not quite. Not quite. Okay? Let's think about this a minute. And you can write this down, not right now. We're going to come back to that problem in a second. So what did we say the derivative of 3y was? 3y prime. Now what if instead of y I had to put f of x? Because they're the same, right? Y and f of x, same thing. They're kind of interchangeable. If I said do 3f of x, the derivative would be 3f prime of x, right? So those kind of match, right? Okay, so now we're trying to figure out the derivative of y squared, right? That's the question in front of us right now is what's the derivative of y squared? What if I would have written it that way? Is that the same? Okay, now think about the problems we did today, or we just got done talking about. What would you do for the derivative of this? When you bring the 2 down in front, then what? Isn't there an inside here? There's an inside here. Times. Now, because of these parentheses, that made you think of that, didn't it? So what's the derivative of y squared, do you suppose?
2y times y.
This is a 1, right? So, doesn't it have to be the same as this? It's got to be the same. These two are the same thing. Y squared and fx squared are the same thing. They're the output. This is 2y, y prime. Here's why. You've got to think of the y as a function. Remember I said u and v were like some x's? U and v are functions of x. Y is the output variable. Y is some batch of x's. Now it turns out in some functions we can't figure out what that is. We can't solve it for y to figure out what it is, but we just know implicitly it's implied. That's why implicitly it's implied that the y is some batch of x's. And so it's like some stuff squared. So we have to do our normal derivative rule, y squared, the derivative would be 2y. So here's the easy way to do this, guys. If you're doing a derivative with a y, you simply do the normal derivative, stick on the y prime. That's what you do. Do the derivative normal, stick on the y prime. So the derivative of y squared is 2y, stick on the y prime. Doesn't that fit with what we did right here? What would normally be the derivative of y? 1, stick on the y prime. You have 1 more, right? So, back to this problem. So this would be 2y, y prime, and then what about over here? You just do normal derivative with respect to x. So this would be 12x squared plus 2. But then what do we want to end up with in our answer? Y prime. So we need to divide by 2y. So we get y prime equals 12x squared plus 2 over 2y. Now here I would take out a 2. Here you should take out a 2 and cancel because you could. You took out a 2 on the top, you could cancel the 2's. Okay? So, what we're saying is, in this thing called implicit differentiation, when we get our final answer of y prime, it will or could have a mixture of x's and y's in it. It might have both x's and y's in the answer. Okay? And that's okay. Because if I now want to do the slope at this point right here, there are two different slopes. So when x is a 4, I'd have to know this y value too. So I'd come right here and I'd put 4 in for x and whatever y value this was, and that would give me my slope at that point. And then here I'd have x is 4, but I'd have a different y value. And so I'd put in a 4 here for x and a different y value, and that would give me the other slope, right? And so curves like that would have to have, okay, slopes. All right, but the main lesson is when you have a mixture of x's and y's, you do the derivative like you normally would, but whenever you do the derivative of a y, you tack on the y. Okay? Now, I promised you, I forgot about this. I should have handed this out earlier. I'll go ahead and give this to you now. I told you yesterday I'd give you your derivative. All right, now, not going to talk a lot about these right now, but so I want to draw your attention. I think I mentioned this. Did I mention this in both classes? Okay, look at the power rule real quick. Derivative with respect to x of u raised to the n power, right? See that one down the page there, about 5 or 6 down? Did I talk about this yesterday? Right? I think I did it one time. Okay, so we're still doing the derivative with respect to x, but u is going to represent our function. It's some function of x. It's some batch of x's raised to a power. So it's kind of like what we're talking about now with y squared. The y is some function of x raised to the power, so we do our derivative. So what do? We bring the power down in front. We leave the inside alone. That's kind of what the u is, whatever that would be, to the n minus 1, and then we tack on the u prime. And that's kind of what we're saying now with the y. We just tack on the y prime, okay, because that would be like our inside, okay. So that's kind of like this. So when we have y squared, what we really have is some stuff squared, right? And the stuff is the y, okay. So we tack on the derivative of the inside, the y prime, okay. That's what we're talking about. So that's similar to all these rules that we have. Okay, we'll spend some time tomorrow going through those rules and looking at those. Okay, so let's say we have this problem right here. So everybody look at that. This is a sideways parabola. Okay, yes, we could get the y by itself right now. We could get the y by itself. And we could, we have a plus minus square root, but we don't have to. And actually, this implicit differentiation is actually kind of nice. Once you get the hang of it, it's really not very hard at all. Okay? So what we're going to do is a derivative of both sides, right? So here we go. So what's a derivative of x? 1. We would never write x prime because that would just be dx over dx. In this problem, we're doing the derivative with respect to x. That's just 1. Minus 2y, y prime, equals derivative of 0, 0. And then we want to do what? What are we trying to get when we're all done? We're trying to get y prime. We want to know what y prime is, right? So we solve for y prime. So we add that over, divide by 2y. I would claim that that is way easier than doing this and then doing the square root and then writing that as y equals plus minus x to the 1/2. And so now y equals plus minus 1/2 x to the negative 1/2, right? And that's your y equals plus minus 1 over 2 square root of x. Now I would claim that those two are the same, right? Because what is y? Y is square, look, notice these two, right? What's the difference? That has a plus minus on it, and down here with the 2 I have square root of x. Here I have y. Well, what is y? Y is plus minus square root of x. So it makes sense that you take the y out and you put a plus minus square root of x in. Those two are the same thing. Okay, the difference is if I want to know the slope right here, I would need to know this y value, right? So let's say this was 9, that would make this point 3, right? So over here I would put a 3, so that slope is 1/6. Over here if I was doing it, I would put a 9, right? I would put a 9 in and I'd get, again, 1/6 plus or minus. So I got 1/6 there as a slope. Here it's negative 1/6, right? And so down here I'd have to put a negative 3 in to this and I would get my negative 1/6 slope, okay? So that's implicit differentiation. Okay, let's do this one. Okay, what's the equation of this look like? What's a graph of this, look like? This is a circle, right? There's a circle. Well, clearly a circle has slopes. It's not a function, but it has slopes, right? So let's do the derivative of this. So the derivative of the left side would be 2x plus 2y prime equals 0. The derivative of 1 is 0. Now we want to get y prime by itself. So we would subtract that over. We would divide by 2y. The 2's would cancel. and there's our y prime. Our y prime will have both x's and y's in it most of the time when we do implicit differentiation.
We don't think we replace 2x with 2y like, you know, like.
Will this be on the gateway test?
Yeah.
Yes.
Okay.
Yes, there will be. Now, they'll be easy to see. Right? All the problems are going to be y equals something, except the ones where you have to do implicit differentiation. The ones that have to do implicit differentiation, you're going to have a mixture of x's and y's. They're going to look different, right? I mean, so it'll be easy to tell which ones you need to do implicit differentiation. The ones that you just do normal derivatives, y equals, right? Most of them will be that. There'll be one or two. I can't imagine there'll be more than two of this on them. Okay. All right, here we go. Let's look at this one. Which, by the way, just so we do a different one, what would the derivative of sine y be with respect to x? Cosine y times y prime, right? I mean, that's what you just do the normal derivative. When it involves the output variable, you do the normal derivative, tack on the output variable prime. Right. Okay, here we go. So let's do this one. Now, this is a particular type of this would be ellipse, I believe, actually. This would be like a tilted ellipse. Okay? But anyway, so we just start, right? We just do the derivative both sides. So what's the derivative of 5x squared? 10x. Right? Now, here's where it gets a little tricky. How are you going to do the derivative of this? Let me give you a little hint. We're going to think of this as negative 6x times y. How do you do the derivative of that? What do you have to do if you're multiplying two functions together? You have to do the product. We have to do the product. We have two functions we're multiplying together. It's like taking negative 6x times f of x. Right? We had a problem like that today. Matter of fact, you had that problem that was x squared times f of x. You had to do the product. Same thing. Negative 6x times y. Now, I would make that negative come with that 6. That'll save you some problems with distributing and stuff. So what do? You do the derivative of the first. What's the derivative of negative 6x? Negative 6 with the y left alone. Plus, I'm not going to write the plus because I know a negative's coming, but plus negative 6x left alone times the derivative of y. What's the derivative of y? Y prime. Right? I mean, derivative of y is y prime. Okay? Now, if that had been a y squared, we'd have put 2y, y prime, right? If that had been a y squared, we'd put 2y. Or what if it had been a y cubed? If it had been a y cubed, what would we put? What's the derivative of y cubed? 3y squared, y prime, right? 3y squared, y prime. Normal derivative, tack on a y prime. All right, anyway, derivative of y is y prime. Plus, what's the derivative of 5y squared? 10y, y prime. Equals derivative of 16? 0. Okay, now what are we trying to get at the end? Y prime by itself. Now we got two y primes. Well, that's okay. All we need to do is leave the y primes on one side and all the other stuff on the other side. Just leave the y primes on one side, so I'll leave them here. I'm going to move those other things over here. So I'll have negative 10x plus 6y over here. I'll have negative 6x y prime plus 10y y prime over here. Make sense? I'm going to move the other stuff over, leave the y primes on one side. Because I can then do what? Factor out a y prime. So I want to group the y primes to one side. That way I can, and then do what? Then divide by that quantity. So I get negative 10x plus 6y over negative 6x plus 10y. Now you could take a 2 out of that. You could take a 2 out of the top and 2 out of the bottom. And so your final answer really should be negative 5x plus 3y over negative 3x plus 5y. Really should be your final answer because you can take out a 2. Okay? The key is recognizing that you have an x times a y, that's a product. That's a product. Okay? And so then what happens is sometimes you get more than one y prime. Once you've done that step, gather the y primes to one side, get the other step to the other side, because then once you have the y primes all on one side, you can take out a y prime. And there you go. Okay? All right, and so if we wanted to know the slope at the point 2, 4, we would put a 2 in for x and a 4 in for y, and we would know the slope at that point. All right, so on your homework, probably revisit 3.1 and 3.2 if you didn't really spend a bunch of time on any of those. But here's the thing. Page 195, if you would flip to 195 real quick. Now what 195 doesn't have is a lot of implicit differentiation practice. So 3.3, I've assigned you a handful of them. That's what we just learned, your implicit differentiation. But remember, that's a small part of the gateway. So on page 195, there's a whole bunch of them. And then it even goes over to 196. Now, I wouldn't go past about number 60, I don't think. No, not even that far. 59, I would only go to about 59. But those are ones that every day I'll say, hey, do some out of page 195. You know, pick 10 or, you know, whatever. And then, or more, if you need practice. But you could also go to those 2 websites I was talking about a little bit. Okay? But you could get a lot of practice if you just stay on page 195. Okay, 195 is going to be a mixture of some chain rule, a product rule, a quotient rule. So that's good practice. Okay? And then tomorrow I'll just ask, hey, has anybody got any question on any out of page 195? You know, and I think I'd skip around too. I don't think I would just go 1 through 10. Right? Because I think I mean, I don't know. It's up to you. But
You know, check in for the PDF or that question generated.
either one. Either one. Yeah. Either derivative practice 1 or derivative practice 3 would be fine.